Guys, welcome to 7.3 logarithms. So hey, really quick before we get started, just a reminder what a logarithm is. So a logarithm is essentially taking the inverse of an exponential function. So up until this point we've been doing things like y equals 2 to the x, right? Well, a logarithm will essentially do the inverse of that, where we swap x for y. So today we'll be seeing things like this: x is equal 2 to the y. Okay, but how we solve those is through what we call a logarithm. So inverse functions, remember that we interchange x and y. So again, just going over what I just said, we have these inverses of each other. So we have the blue graph here and the red graph. These things are inverses of each other. They're always, if you have an inverse, it'll always flip over this line y equals x. Okay, so it'll be mirrored across that line. The distance at a right angle to that line will always stay consistent. Okay, so for a logarithm, the big takeaway here, you guys, is just how these logarithms work. Okay, so if I have a log base b of x, that's how you would pronounce that, equal to y, what that means is it means take the base to the y power and set it to equal that x. So another way that you could write this logarithm is b to the y is equal to x. If you want to put some numbers in, we can look at this example here. Okay, so for example, if we have log base 3 of 27 equals y, we're saying 3 to the y equals 27. And once we do that, we can kind of use guess and check to solve that, right? 3 to what power gives you 27? The answer to that would be y is equal to 3. Okay, so eventually we'll be able to plug those things into our calculators and do a bunch of fun stuff with them, but for now we're just identifying. So example 1, they want you to write this as an exponential function. So we're going to take 4 to the second power and set it to equal 16. All right, then you try 1b on your own there. All right, hopefully for 1b, what you're getting is 3 to the 6 is equal to 729. Okay, so we're writing that in exponential form. Then we want to go backwards, right? So with logarithms, the base is always a little number. So it's funny how the big number becomes a little number. So we're going to say log base 4. So there's the base of the answer, 64, is equal to the power. Okay, so this over here will be 3. So it's always the log. This is always going to be your base. This is always going to be your answer. And this is always going to be your power. So the base to the power equals your answer. Okay. So let's do another one here. This will be log base 125 of 1/3, that's the power, is equal to 5. So log base 125 of 5 is equal to 1/3. If you take 125 to the 1/3 power, you'll get 5, right? Okay, so example 1 and 2, you're just writing things in log form and exponential form. Example 3, they want you to actually evaluate it. So if it's not equal to something, you could say it's equal to well, you could say y here. So 3 to the y is equal to 81. So 3 to what power is equal to 81? Y would have to equal 4, because 3 to the 4th power is equal to 81. Same deal on 3b. We have 1/2 to some power y is equal to 256. Okay, you can start using guess and check here. You can also rethink this, and you can put this both in terms of 2, which you can always do. So this is the same thing as 2 to the negative 1 to the y is equal to 2 to the 8. I know that the 8th root of 256 is 2. You may not know that. So you might have to just take a bunch of, you might have to take, 256 to a bunch of different powers to find 2. You might have to do like the 6th, the 7th, and then eventually you'll find that it's the 8th power. The 8th root, I should say, of 256 is 2. So then I can write this as 2 to the negative y is equal to 2 to the 8, because negative 1 times y is negative y. Therefore, negative y is equal to 8. So y is equal to negative 8. And in your text, they might use y or they might use x there when you're solving that. It doesn't really matter which one. It depends on how they look at it. I guess they don't even use an x or a y, so don't even worry about it. But let's look at example 4 now. Okay. Oh, and this is kind of important. The parent functions of graphs. Notice that whenever you have a base to some power, if you take a base to some power, you're going to get a positive number out, right? Assuming that your base is positive. So if your base is positive, you're always going to have this positive number coming out for your answer. Therefore, the domain of this thing, okay, if you set it up like this, y is equal to log base b of x, the domain here will always be positive. Positive real numbers. The range in this case would be all numbers. You can plug in whatever you want. All real numbers for the range. And yeah, that's essentially all that you need to take away from the parent function. So let's look at this. So if we have y essentially is equal to log base 2 of x, you can think of this in two ways. You can say that this is like 2 to the y is equal to x, right? So write it in exponential form. And then what I would encourage you to do if you're graphing these, which is what you're doing in example 4, is I would encourage you to just choose y values. Choose these guys. So let's do that. If we do that, let's see what we get out here. So if we choose, let's just choose, for instance, what happens if we choose 0? If you choose a 0 for y, 2 to the 0 is just 1. Okay, if I choose a 1 for y, 2 to the 1 is 2. If I choose a 2 for y, 2 to the 2 is 4. If I choose a 3 for y, 2 to the 3 is 8. If I chose a half for y, let's see, or do I want to choose a half? I don't know. I already chose 0. So let's just get these in. So at 1 comma 0 we have this point. At 2 comma 1 we have this point. At 4 comma 2 we got a point, and at 8 comma 3 we have a point. Okay. Let's see here. What else? Well, what happens if I choose a -1 for y? 2 to the -1 will give me a half, right? Because 2 to the -1 is the same thing as 1 over 2 to the 1, which is 1/2. So at 1/2, which is somewhere in here, I'll be at -1. And if I plugged in something really ridiculous, like what if I wanted negative, well, this isn't that ridiculous, but what if I wanted -4? Notice what happens if I plug in a -4. 2 to the -4 is equal to 1 over 2 to the 4, which is 1/16. So at -4 on the y, I'm at 1/16 on the x. I'm really close here, so I got this kind of thing happening. So it's going to approach this axis, but it's not going to ever cross it. Okay, so that's example 4. They want you to graph these things. And then they also may want you to put the domain in the range. So here the domain is all positives, the range is all reals. Okay, so let's look at another one, 4b. So for this one, again, I would write it in exponential form. So this is the same thing as 1/8 to the y equals x, right? So if I plug in some values for this, let's go ahead and plug in some things. If I plug in we can always start with 0. Anything to the 0th power is just 1. So at 1 comma 0 we have this point. Then if I plugged in what's crazy about this one is if I plug in like a let's just do this. If I plug in a 1, I get 1/8. Okay, so at 1/8 on the x, I am at +1. Something like that. Okay, if I plug in a 2, I'm at 1 over 64. So I'm like really close to 0 and I'm up at 2. So you kind of get the point of what's happening there. What if I plug in a -1 for y? If I plug in a -1 for y, I'll be at, so 1/8 to the -1 is like 1 over 1/8 to the first power, which is equal to 8. Okay, so at -1, I'm at 8. So over here, I'm going to go 8, -1, and I got that thing happening. So it's kind of this pattern here. A little different, right? Okay, so that's 4b. Now, for the last part of this lesson, just 2 more examples, guys. We have transformations, which you can do this on Desmos, and I highly encourage you to do this on Desmos. But what you can see is, in Desmos, if you modify something inside the function, okay, so in this case, it would be in the parentheses in the log function, then we know we're going to have a horizontal movement. Okay, whatever makes that go to 0 is how it's going to shift, just like with every other graph. If something happens outside the function, like the k, that's just going to move things up and down. And then a will tell us the orientation and the shape. If a is less than 0, then the graph is reflected across the x-axis. Okay, it's going down. If it's between 0 and 1, the graph is compressed vertically. If it's greater than 1, it's stretched vertically. These are the same exact transformations that happen with all graphs, right? They're just looking different because they're in a log function. So here we have, essentially we have something that's like this. Y, well, let's write it like this. 3 to the x power is equal to y. Let's not write it like that. Sorry. 3 to the y power is equal to x. If I were to graph just that, we know kind of how that would look, because it would look a lot like when we did 2 to the y equals x. So it looks something like this picture here, right? But now what we're doing is we're shifting this 2 to the right, and then we're stretching it. Okay? You don't fully need to know that. What you could do is just continue doing what we've been doing, and we can write up something new. We can say 3 to the y is equal to x minus 2. But then what we have to consider with this thing is that we have to multiply our answer by 2. So we have to multiply whatever we get there by 2. Okay, so in order to do that, let's make a table. If I make a table here, we have x, we have y, and then what I would encourage you to do is make more than just x and y. I would encourage you to multiply by 2. So what happens with x and y and 2? So if I plug in, and again, we've been plugging y values in, right? So if I plug in a 0 for y, okay, then my x value would have had to have been 3, right? Because 3 to the 0 gives me 1. So x minus 2 there, I would have to have a 3 there in order to make that a 1. Okay, and then if I multiply this y value by 2, right? Because if I put a 3 in, I get a 0 out. Multiply that by 2, I get 0. Okay, so let's try something else here. What happens if I plug a 2 in for y? Okay, so I'm saying 3 to the 2 is equal to x minus 2. This is 9 is equal to x minus 2. So x, therefore, is equal to 11. Okay, but then I got to multiply my y value by 2. So then I really have 4. Okay, so my points here, when I go to graph this, are going to be at 3, 0. And then I'm going to have another point at 11, which is, man, it's already off my chart, isn't it? 11, 4. So I'm somewhere in here. Okay, and what's going to happen is this is, I mean, this is only 2 points, so this isn't a great example, but I don't want to take too much time here. I could put in some numbers in between. They're not going to turn out very nice, but what's going to happen is this thing is going to approach this 2, but it's never going to cross this 2. So it's going to do something like that. And the reason for that, what's helpful with transformations, is the whole graph from something that looked like this is shifting to the right. Okay, it's shifting 2 places to the right. And then we're vertically stretching it, so it's getting longer. All right, so you could plug in some more values there, and I would encourage you to do that, and maybe use Desmos a little bit if this is getting a little bit too much and confusing so that you can see it, but essentially that's what you have. Okay, example 6. I don't know why I didn't give you example 5b. Example 5b is a good example as well. If you look in your textbook, I don't know if I have it in your notes, but example 5b, I encourage you to try that one. And make sure that you multiply on 5b. So on 5b, just so that you're aware, because you'll have one like this on your homework, you have y is equal to 1/4 the log of 1/2 of x plus 1 minus 5. Okay, what you need to do on this one is you need to, choose your y value again, get your x value out, then multiply by multiply by 1/4, not negative. And then at the very end, you'll subtract 5. Okay, so what that chart will look like, just so you know, and I would make a chart that's like this, x, y, and then maybe I would say times 1/4, and then I would say minus 5. Okay, so if I plug a 0 in for y, I get a 0 out for x on the base function. Multiply by 1/4, I get 0. Subtract 5, I get negative 5. If I plug a negative 1 in for y, I get a 1 out. Okay, if I multiply my y value that I plugged in by a 1/4, I get negative 1/4. If I subtract 5 from that, I get negative 5 1/4. Okay, and I know I'm moving fast here, but if I plug a 1 in for y, I would get a negative 1/2 out for x. Take my 1 and multiply it by 1/4, I get a positive 1/4. 1/4 minus 5 is 4 3/4. Okay, so those are some points. And then you would use these points. 0, negative 5, 1, comma, negative 5 1/4, negative 1/2, comma, 4 3/4. So I encourage you, if you get to these harder logarithms and they want you to graph these, to both put them into Desmos, but then come back to this video and maybe see how I set this up. So example 6 says, write an equation for the inverse of the function. So to do that, this thing would be, so we're going to swap x for y, so we would say x is equal to 0.5 to the y. And that is technically the equation for the inverse, but then we have to solve this for y. Okay, so how do I solve this for y? And this is where you get into the question of, what is a log, like how does this relate to logarithms, right? So if I'm solving this for y, what I need to do is I need to take the logarithm of this. Okay, so I can say here that y, or the power, is equal to the log of 0.5x. Okay, so, but if you wanted to use the loop method, maybe you write it this way. Log base 0.5 of x is equal to y. So you have this to this power is equal to this, and that works. So when I'm solving for y, you're going to want to use a logarithm to show that. All right, guys, that's it for this lesson. We'll do some of these in class for sure. There's a lot of resources out there as well. A lot of things on logarithms on Khan Academy and such. So we'll catch you guys soon.